The problem statement from GATE Physics 2011 reads as follows. Consider the following circuit. In this circuit, we have been given an operational amplifier with a few resistors and an input voltage, and we're taking the output over at this node. The question says, which one of the following correctly represents the output V out corresponding to the input V in? So the input we are giving is a triangular waveform, and we are required to find the output waveform. Only one option is correct among the possible 4 options. Before we try to go ahead and solve this problem, we just need to do some pre-checks so that we can apply the standard op-amp formula or not. So first we talk about the ideality of op-amp. The question is silent about it, so we'll just assume that this is an ideal op-amp. What this would mean is that we'll ignore all, we'll assume that the input impedance is high, infinity, and the output impedance is low, and other related things. Second is the nature of feedback. So first we try to identify whether there is a feedback in the system or not. So we can see that the output node over here is talking to the non-inverting terminal using this 4K resistor. So there is a feedback. What kind of feedback? Since output is talking to the positive terminal, it's a positive feedback. And we'll talk a bit more about positive feedback in the next slide. Right, so as the name suggests, operational amplifier, this is used to perform some operations, and one of the very simple mathematical operation is comparison. So in this, so on the left in blue, you can see an operational amplifier A. These are the saturation voltages plus VCC and minus VCC, and we are applying a reference voltage to the negative, to the inverting terminal, and we are applying an input signal to the non-inverting terminal over here. So what it will do, it will compare, the output will be minus VCC if the input voltage less than the reference voltage. On the other hand, if the input voltage is higher than the reference voltage, you can see the output will quickly jump to the plus VSAT, which in this case is plus VCC, and this is what we mean by comparison, which this is summarized over here in the purple box here, and this is how the waveform will look like. But this is not the only application of the operational amplifier that we can have. We can have certain other mathematical operations like integrator, differentiator, adder, and others, and logarithmic. So those are implemented using a negative feedback. So you can see the output node here is talking to the negative terminal, hence this is termed as a negative feedback, and usually the outputs are stable in this configuration. And the other possible feedback is the positive feedback, where the output is talking to the positive terminal, and in this case usually it gives unstable outputs. But these circuits are also useful in the sense that they are oscillators, since the output will not remain stable, right? So what that I'll mean is that the output will keep on fluctuating like this, in this positive feedback output. This is positive feedback output. So output will keep on fluctuating, it will keep on oscillating, and hence we can use this to create some square or rectangular pulses. And one of the common examples is the Schmidt trigger, which happens to be the problem statement here. So you can see that the output is talking to the positive terminal, right? And this is the circuit diagram, by the way, of a Schmidt trigger, and the input is applied to the inverting terminal over here. Oh, now we are and this is the input waveform that we are given, right? And if you notice that in all the four options, the starting voltage was plus 10 volts. At t equal to 0, the starting voltage, so this is V out. This is V out as a function of time, and the starting voltage is plus 10 volts. This is given to us, and we are required to populate the what time with time how does this change. So let's just start with that information that we already have. So we know that V out is plus 10 volts. So I am assuming, so first what I'll do is that I'll only try to solve the problem only for when we are just starting over here. Okay, we are just starting from this region. Okay, so let's just, and even before that, what I'll try to do is that, since we know that the output voltage is plus 10 volts, so what I'll do is I'll also plot here with time V plus. This is the voltage V plus. So I'm plotting this over here. So if I try to calculate V plus at when V out equal to 10, so you can see this is a potential divider. So since this is an ideal amplifier, no current will flow in. So this is I equal to 0 here. So whatever current is flowing here, so whatever current is flowing over here, same current will flow over here, and you can clearly see this is a potential divider. So I can say V plus will be nothing but 1 times V out, that is 1k times V out over 1k plus 4k. So that will come out to be 1 by 5 V out. So V plus will always follow V out in the sense by a factor of 5. So if the V out is 10, right, so V plus would be simply 2 volts. So this is 2 volts. Okay, now let's analyze, now let's move forward in time, and let's see what happens when the time increase, and with time V in increases. So we can say that case 1. So what will happen is that now this will be treated as a reference voltage. I told you in comparator, then the V plus and V minus are compared. So V plus for case 1, we can say V plus is plus 2 volts, right? And we are considering case 1 when V in is less than plus 2 volts. So I am interested only in this region firstly, because that is the reference that has been set. So what's happened, V in is less than plus 2 volts, and because this was the reference, V plus is plus 2 volts. So now I'll try to analyze how will this op-amp behave. So you can see that so this is the case, and this implies that V in is nothing but V minus, so V minus is less than V plus. So V in is less than plus 2 volts and V plus is plus 2 volts, right? So we can say that this implies V out would be plus VCC. That's the response of a comparator, right? So V out will remain as plus VCC over this purple time scale. So what I'll do is that, so this will remain, so I'm drawing this here. So V in will remain plus VCC, and correspondingly V plus will also remain as plus VCC till this time. Now what will happen is that now we have reached over here, we are here. So now let's try to understand what happens case 2. Remember, V plus at this point is again plus 2 volts, and now V in has exceeded plus 2 volts. This means V minus has now become more than V plus. Now since V minus is more than V plus, this implies now V out will flip to minus VCC. So let's do that. So V out has now flipped to minus VCC. Minus VCC is minus 10 volts. So V out will simply go from plus 10 to minus 10, right? And correspondingly, because this is a potential divider, V plus will also flip from plus 2 to minus 2. This is minus 2, and this voltage is minus 10 over here. Okay, so now what I am going to do, so now this changes things. Now V plus, which is the V reference, will now become minus 10 by 5 using this for potential divider equal to minus 2 volts, which I have plotted over here. So V plus has now become minus 2 volts. Now this will become the reference. So now what will happen is that, let's now do case 3. Case 3 I am doing in black. So case 3. Now at this junction itself, now V plus has become minus 2 volts, and V in this region, we are still in this region, V in continues to be greater than, now this is the new reference, right? So I can take so this is the new reference. So when V in is greater than minus 2 volts, this implies V minus will remain more than V plus. Now the reference is minus 2, so for the time, this means this much time, right? This is the case 3. So in case 3, you can see that V in will remain higher than minus 2. This implies V minus will remain greater than V plus. This implies V out will be minus VC, and correspondingly V plus will be minus 2 volts. So what this would mean is that over the red time scale, which ends over here, right? So our V out will remain minus VC. V out will continue to be this, and correspondingly V plus will also continue to be minus 2, right? So now let's consider the last case. What happens when now V in crosses this threshold? right? So I'm talking about just over here, right? Just when it has crossed. So this is again in purple. So again case 4, V plus continues to be minus 2 volts, right? You can see in this waveform. And now V in has just become less than minus 2 volts, maybe minus 1.9, minus 1.95. So again we see V minus has become less than V plus, right? So this implies again by the function of comparator, because V plus is now higher than V minus, V out will again swing to plus VCC, and V plus now will become plus VCC by 5, which is plus 2 volts. So now we see that the output, just as soon as over in this again purple dot, this will again go to plus 10 volts, and this will again jump to minus 2. Now this is the same scenario that we had started earlier. So now what we can do is, now what simply will happen is that it will keep on oscillating. So this is the, so one threshold will be this. Note that it changed at green, right, which is denoted by red here. At plus 2 volts it will go down, and then again when it crosses minus 2 it will go up, right? So effectively you can say that this has two thresholds, one at plus 2 and one at minus 2. So it falls when it crosses plus 2. By the way, this is also known as hysteresis. We'll talk about in the next slide, but you can clearly say that when V in crosses plus 2, the output falls, and when V in crosses minus 2, the output rises. So we see that. So when V in crosses plus 2, the output should fall, which is falling. When V in crosses minus 2 in this direction, the output should rise. So this is what's happening over here. If you see V in at plus 2, there's no change in happening in plus 2, so this is not the correct option. Again at plus 2 it should fall, plus 2 it is falling, and at minus 2 it should rise, so it should have risen over here, so this is also not correct. Similarly at plus 2 it should fall, so this is also not correct. So option A satisfies that at V in equal to plus 2, the output will fall, and V in and minus 2, the output will rise. This is also known as hysteresis, because you have two different thresholds of depending on the direction of the V in. When V in is rising, the threshold is plus 2. When V in is falling, the threshold is minus 2. And this is the typical response of a Schmidt trigger using a positive feedback operational amplifier. So option A is the correct one. Thank you for listening.